I said, okay, y'all, let's talk about some CNC stuff, shall we? Actually, let me, I gotta go talk to this guy real quick. I'm gonna put this PowerPoint on Blackboard too. Okay, this PowerPoint you will not be quizzed over, but it's the basics of like G&M codes and the basics of CNC and where it came from. That will be information that you're going to want for to help your labs make sense. And I want to, hey, if you're going to be on there, put some headphones or something in, okay? What does CNC stand for?
CNC.
Computer numerical control. Basically what happens around that, so this is like World War II era, a couple years after, but there was a need to mass produce machine parts that were very precise, right? Airplanes and whatever else were going in the Cold War. And they had these ways, they started developing ways of numerically controlling a machine that would mill or drill or you know, whatever, a piece of metal for. Hello? Hi, I'm in class. Yeah, go ahead. No? Okay. Okay. Oh, yes. No, I'd like to go. I will get on that as soon as class is over. Okay. Okay. No idea. Thank you for telling me. All right. I'll talk to you later. Bye. What? What were we talking about? Yes. So they used to have these old this old punch tape, right? Before computers were around. And let me, you know, yep, yeah. Uh, so anyway, all these different lines would be some kind of code that would tell the machine back at that time to do this, move the tool in this way, move the tool in that, and it was very cumbersome, but it worked, and it created accurate, repeated, the same machine part every time. What am I doing? So this is the old punch tape. Now we're getting into computer numeric control. So then they had these computers linked up to the machine that would do the same thing, and they had to develop these codes, right, to input input into the machine to tell it exactly where to go, where to put the bit. Same as a robot, right? And we're going to get into the G codes and all that, but robots are dumb. CNC machines are dumb. You have to tell it exactly what to do and when to do it and in what order to do it in. All this stuff is kind of cool but irrelevant. Machining components with repeatable accuracy, unmanned machining operations, so it was quicker, more accurate, and you didn't have to pay 50 people to produce the same amount of parts as you could have a machine with one person just loading parts, hitting the buttons, and off you go. So there's different kinds of milling machines. This is a vertical mill. A mill will take, you know the difference between a mill and a lathe is? Right.
You have X, Y, and Z on the mill.
Yep. So whether the machine is doing on a lathe or the machine is doing the removal of material or a person is, the part itself is spinning, right? On a mill, the tool head is spinning and then you move the part around to take out material however you need it. This is a horizontal mill. I'm going fast through this first part because I want to get to the programming of this stuff. There's an XYZ Cartesian coordinate system. You guys should be experts on that by now. Blah, blah, blah. Unless you want to review any of this, you're good with coordinate systems, right? Okay. Don't be afraid to say, let's review that. Okay, a couple different types of milling, slab milling, face milling, and end milling. So I think of like slab and face milling as kind of shaving pieces down, where end milling, you're doing more precision, taking smaller chunks out at a time. And here's an example of a part that's been end milled. Ooh, straddle milling, slotting, slitting, and form milling. That's cool. T-slot. First cut, second cut. This is all just kind of for your info if you guys want to go back through and learn more about this stuff. Okay, this stuff's kind of cool. So here's a loop of servo motor. You guys know what servo motors are and how they work? Usually a DC motor, but the difference between a regular motor and a servo motor is servo motors have feedback. So there's encoders that sense position, and they know exactly what degree rotation the motor's at all times, and they know where everything's positioned, and you have feedback back to that system. So you have an output and an input all kind of in one motor setup. Those are usually controlled by some kind of servo drive or servo amplifier, and you will see servo motors on the trainers that guy is working on, right? Yeah.
You have servos that see over 60 degrees.
Yeah, they all do. It's just
some I know,
like give me an example.
Like
Must have been manufactured that way, you know, because like the servo motors that you're going to see and the servo motors that control the robot arms, they can go more than 360 degrees. I guess it depends on the application, because a robot has all sorts of cables and hoses, like pneumatic hoses and stuff inside of them, right? So you don't want to keep rotating, and you can input faults into the teach pen that will disallow it, stop that from happening. But there's some worm gears on these trainers back there that move a piece that's just an arrow with a tape measure. And you'll be able to see on the display exactly where you're at on the tape measure. And also you could say, okay, I want to move it 10 inches this way or 2.6 centimeters that way, you know, and you can write a code on the screen that'll tell it to run through this sequence of events, and it'll do that. It's able to do that because it keeps track of how many pulses. So like this slide says there's 500 pulses per revolution in this example. If you're at 250, it knows you've spun 180 degrees, right? The pitch of the lead screw has a lot to do with that. And that's a big part of the problem that we're having with those machines right now. And the reason that we had this guy come up here to help us with those machines is because I could get everything to work okay, but the parameters are so jacked up. Those things are 20 years old. And people have screwed with the parameters on there so much that if you tell it to move 2 inches, or if you jog it 2 inches, it'll tell you on the screen that you moved 160 feet, you know, like it just like that stuff. So you actually have to measure the pitch of the screw and input that as a parameter, all this stuff that I don't really know how to do. So that what's showing up on the screen and what you're doing on the piece of equipment is jiving. Anyway. Calibration, yeah. Yeah, but the bad thing is, and I couldn't believe that there's not like on the internet somewhere, some file with basic parameters that you can throw in there, you know, just download to the equipment. That's what he's trying to create. But and there's hundreds of parameters on those things. So this is an example of a file that you'll see on those things. And each and every one of these lines is called a block. Each and every one of those lines tells the machine to do something. And it will start just like on your teach pen on the robot. It'll start at the top, go left to right, and work its way down. Rinse and repeat. So all these O's and N's and M's and G's and H's and M's and X's and Y's and Z's, those all mean certain things. You're not going to have to memorize any of these for this class. You're not even going to be tested on this stuff other than doing the homework that's in the labs. Were you both here on Monday? Okay. And then Justin was here and we changed them from quizzes to homework. Okay, good. So each letter address relates to a specific machine function. G and M are the most common. G specifies machine preparations, like we're going to be in standard or metric mode, or use absolute versus incremental modes, which we'll talk about later. And then M, which is miscellaneous, all sorts of crap. You already know the coordinate system, units, incremental, absolute. We'll talk about that in a minute. Blah, 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 blah. Preparatory codes. G codes, initial machine setup and establishing operating conditions. N codes, program line number to be executed by the MCU. Axis code, X, Y, and Z, pretty common sense. On those 4 pieces of equipment, you will only have the X axis. We're moving that thing back and forth in one direction. So plus X or negative minus X. Even though it will show you a Z axis on there, we're not using it. Feed rate and speed, spindle speed. tool codes, and miscellaneous codes. So here's a block, and that's this guy. Can you see my cursor? This is a block right here. Block is just another way of saying one line of code. There are restrictions though. One block can contain only one tool move. One can contain any number of non-tool move G codes. One feed rate, one specified tool or spindle speed. Block numbers should be sequential, so that's this guy, and 135. Think of it as like line number 135. Program start flag and program number must be independent of all other commands or on separate lines. And the data within a block should follow the sequence shown in the above sample block. Okay, so N3 in this case is, think of it as line number 3 or the sequence number. G2 is a preparatory function. X, Y, and Z tells it where to go. I, J, and K is the distance to the center of a circle. And then F, feed rate, S, spindle speed, T, tool, and M is miscellaneous. Here's some commonly used G codes, G00, 01, and 02. G00, so you're prepping the machine to say, okay, I'm going to give you an X, Y, and Z, and we don't care how it gets there. G01 is a linear interpolation. So we want you to get from A to B in a straight line. And G02, specified by I, J, and K, which will give you the center of the circle, is you're telling it to go in an arc. So if you needed a round piece of material cut out, you would use G02. And here's some more examples. Huh? How long? Did you do CNC in high school? Cool. Wish I was that cool. Where was that, Morton?
Yeah.
Where'd you go to high school? You did too? Good grief. Did you know each other? Were you guys like best friends? Did you guys go to homecoming together? Oh.
Best prank ever. Someone nominated me the biggest nerd in my class.
Did you get it?
Nope.
Oh.
But they made us all stand on the track and football field. They were told me now. All of my terrible friends were like, "Yeah, we're gonna vote for you and Andrew. Fuck yeah, let's do it." What do you do?
I'd have voted for you.
I'm sure you would have.
Ben would have voted for you. It's annoying. Just a popularity contest anyway. Which is why I was homecoming king.
So popular, Zach. So popular.
I was not. Yeah, I was not. But I did go to what was the end of the year one where only the juniors and senior prom. I went to prom sophomore year.
Ooh.
Got asked by a junior.
You got asked?
Oh yeah.
Zach's on shit.
Mm-hmm.
He was like, I don't know, I'll think about it.
Mm-hmm. Let my people talk to your people.
Oh, yeah, I got a list of people on the line. That's all.
Okay. So here's an example program. Drill a hole on a CNC vertical milling machine. So this is the home position, which is established either by default or where you tell it to in the parameters. And then if I remember right, we're going to tell this to go over the top of this hole, go down and drill, and then come back up. Oh, I guess it runs through it. Z-axis, rapid move just above the hole. 3, turn on the coolant. 4, turn on the spindle. Spindle is basically the tool, the thing that spindles. Z-axis speed move to drill hole. Z-axis move out of hole. Turn off the spindle, turn off the coolant, and wrap it home. I think there might be a mistake in there because it said, yeah, this number 2 I think should say X and Y axis rapid move to just above the hole. And then Z would be the drilling motion. Oh, I bet. Because the feed rate was too high. Yeah, and we actually have a couple milling machines that will, you'll see. There's an assignment where you can take make a little ICC or something. I don't remember.
They didn't have like the technology. They had a welding class, they had those classes, and then they had some like they had a
Okay, here's the program. Still got our spindle is over here in the home position. 0, 0, well, we'll go through this one by one. 0, 0, 1, number assigned to this program. Pretty cool. N005. We started with line 1, that's initializing. Here's a program number 1. That's basically what we're instructing the computer. Why did we jump to 5? And then look, the next one is 10. Why do you think that is? It allows us to go back and add lines in between, basically. It's just common practice. So N005 is a sequence number. G54 is fixture offset. G90, these are all initializing preparatory codes. Absolute programming mode. Spindle speed set to 600 RPM. Spindle on and clockwise. It's important. You don't want your tool to run backwards. I'm going to do any cutting. I don't know if it gets into absolute versus relative in here. I guess if we come across that, I'll explain it again, but absolute versus relative means where we're at. We just told it we're doing absolute here. That's what we're instructing the computer to do. So if I tell this to move in the X direction of -3 inches, and let's say that's here, it'd be better if I do this. So we're doing X and Y. I'm doing the best I can. So if we put in there an instruction that says X -3 and then Y -2. So here's a block, right? We did X -3, X -2. Where's the spindle gonna move to? Somewhere right in here, right? Absolute means if I go X -4, so I'll write that first one down here. And this is not going to be correct. There's other codes that we have to put in there. But The first move in this line was x minus 3, y minus 2, right? Now we're here. We told it in this line that we're doing absolute, which means if I then go x minus 4, y minus 4, it will move to minus 4, minus 4. Somewhere in here. Make sense? That's absolute. That's relative to 0, 0, 0. Okay, this point right here. If we do relative, that means the next, it accumulates as it goes. So it's going to take this next line, this one, and it's going to relate it to this one rather than the home position. Right? So instead of this, you're going to go minus 4 this way and minus 4 this way. And you're going to end up down here. You see the difference? Okay. The G90 is establishing we're doing absolute, which would be the first example. Make sense? Next block, G00, rapid motion. Okay, where are we telling it to go? So we're in sequence number 10, G00, we're telling it to go rapid motion. Where do we want it to go? We want it to go in the X direction 1 and in the Y direction 1. Okay, and my previous example doesn't really work here because home was way over here. It doesn't make much sense. But this example is telling us that that is X1, Y1 right here. We told it to go there in a rapid motion. So just machine, go quickly to this spot. Yeah, if I remember right, the actual 3-axis MCO machines do it front and to the left. I don't remember if that zeroes it out or if it starts like at. And initialize it like that. Makes sense. Okay. Number 15. What do you think G43 means? Tool length compensation. I'm not really sure what that means. Other than to tell it exactly where the tip of that tool is. Which you would probably have to use that if you didn't initialize it like you were just saying. Kind of like when we did tool frames with the robot, told exactly where that thing was. The default was right in the center of that end effector. HO1 specifies the tool length composition Z.1 from 0. Okay, so you're compensating it this much, and you're telling it to drill 0.1 inches from 0. And M08 says turn the frickin' coolant on. So we save our tool. And that doesn't look like 0.1 of an inch to me, but it's okay. G1, straight line cutting motion. Oh, that last one then must have just been the compensation. Okay. So this is actually your drilling motion, 3/4 of an inch. So line 20, G01, straight line cutting motion, and go down 0.75 inches from 0. at a feed rate set to 3.5 inches per minute. It's pretty slow. And I mean, you understand what that means, right? In 1 minute, if you started it, in a minute, it will have gone down 3.5 inches. N025, sequence number 25, G0, 0, I'm assuming is straight line cutting action the other direction. M09, and assuming that means turn coolant off. G00, rapid motion. Z coordinate 0.1 inches from 0. You're telling it where to go. And then M09, cool them off. Then line 30, G91, incremental programming mode. G28, 0 return command, XYZ coordinates at 0. End of program. Pretty simple, right? Here's where it gets a little tricky. Now we're dealing with tool size, 0.25 of an inch, feed rate, 6 inches per minute, cutting speed, 300 RPM, tool start position, 2, 2. That's right here. And our programming is in inches. Okay, so we're going to cut this solid line piece out. We have to put the tool in the path of the dotted line. So now that the tool size comes into play here, it doesn't get so simple anymore. We know the dimensions of this piece is the 5x5 triangle. And we know the radius of this little guy, which starts at 2.5 inches, the radius is 1 inch. So here's how we do that. We have to do a little math. And I think I'm gonna double wide this thing. $76. Hopefully you can read that somewhat. How do I hide this thing? Ah! How do I hide this thing, smart people? How do I hide this? I don't want to. If I put in present, I want 2 of these because I want to. What the? What are you? What the? What are you doing? Usually interact that. I don't know. Question. Well, that was no help.
Can tell you. $10.
Ooh.
Yeah, I thought it was pretty nice.
See?
No, no, I don't work that way. Homie, don't play that way.
Millions in a day.
Okay. Okay. Set up the programming parameters. We're going to tell it to program in inches, use absolute coordinates, feed in inches per minute. So that must, G94 must mean 6 inches per minute. Spindle speed in RPM. Spindle counterclockwise rotation. Next line. N020 G17 moves in XY plane. Use full circle interpolation, feed rate, spindle speed, tool number, flood coolant on. Here's where it gets tricky. Linear interpolation, target coordinates, X 3.875, Y 3.698. How did we get to those numbers? It tells you down here. Whoops. Tells you right here. But why are we taking 4 minus 0.125 inches? Remember, we started at 2, right here. Point number 1, we're going to go X 3.875, and Y 3.698. Any ideas?
0.125.
Yeah, so if this is 0, 0, and this point is 4, 4, we need to come back this way, half the size of the drill bit, right? And you remember the tool size is 0.25 inches. Half of that is 0.125. Make sense? So our X is going to be 4 minus 0.125, which is 3.875. We're telling it to go from here over 3.875 inches. We're going to tell it to go this way, 3.698 inches. Where do you think we get that number from? Tangent of 22.5. That angle. Basically what we need is this distance right here, right? Right. Uh-oh, you guys learned a lot about triangles with me, didn't you?
Unfortunately.
Unfortunately. Okay, so we need to know, basically, we don't need to know this distance. We need to know this distance, right? This is what we're subtracting from 4. Let's call this one Z, because I'm cool. All right, so basically we have this triangle that looks like this, this. We need to know Z. How do we know what angle this is?
Well, we know the right angle is not there.
It's 22.5, but how do we know that?
Something about 8 degrees.
it all comes down to triangle relationships. So what this thing is showing us, and all I'm doing is copying this over here. This is a 45. And then you have this little diamond piece here. And this guy right here is half of this. Take that line off of there. Is this angle exactly the same as this angle?
Yeah.
Yeah, it is. Yep. So this angle is a 45. What we need is this, right? And so that 45 divided by 2 is 22.5. And we need to know this distance right here. So that's where we get this triangle from. So 1.25 divided by a tangent of 22.5 will give us this little distance that we have to subtract off of 4. And that is 3.698. Okay? So if we put that into the program, it'll bring us right here, which then sets us to cut in this direction and leave this line untouched, right? That's the cutting edge. Cool. So then, how do we get up to here? 5? Just 5? Won't that put us like right here somewhere?
You need to move 5 plus.
Right. 5 plus the 1.5 plus twice. 5 plus 5 plus this distance. This is 0.25. Right? So we're at 5.25. How do we know what this distance is? Isn't that what we just figured out? It's whatever 0.125 divided by tangent of 25 is. 0.302. I'm just guessing right now because I haven't seen the next slide yet. But I'm guessing it's going to be 5 plus 0.302 plus 0.25. So it'd be 5.552.
Because you're saying that the distance between the cutting edge and the center of the tool. So the tool size is 0.25 inches. You don't even have to do half that point, right?
I think I got too much crap on here. Let me get. Did we tell it we're doing relative or absolute? Relative would be easier, wouldn't it? Okay, we know we got 5 here. That brings us to this spot. And we've got 0.25. No, 0.125. Is that what you were saying?
Yeah.
We got 0.125 there. And then we need this distance here. shit. Just erased everything. And then we need this distance. So that's going to be point. All it is this. 0.125 divided by tangent of 22 and a half, right? That number is 0.302, right? Am I thinking about that right? Yeah. So if we add those up, it's 5.
22.5 is the degree. So put that in parentheses under.
So what we end up with is 5.427. Are we done? No, because we're in absolute. That would be moving it just this distance. We're moving it in the y direction. So where was this y point at? 3.698. So that's what we have to add to it. 3.698. $9.125, and then the same x coordinate, correct? 3.875. And you understand we had to add this because we're in absolute, right? All right, let's see if we were right. Boom. Boom. 9.125, bitches. I think this is fun. You guys are gonna have to do this, by the way. What? Oh, so then we have to tell it, go to x 5.634, y 9125. Are you confident you can do that? Basically, we're figuring out what 0, 0.1, 0.2, 0.3, 0.4, and 0.5 are. Everything else is just an instruction to tell it how to cut, right? So on this slide, you want to work through all these, or do you think you have a handle on it? Yeah, okay, let's do one more. Okay, so if we're doing this, let's keep track of it. So 0.0. This is just a reference to know what the tool size is and the feed rate and all that. I just want to write down what we're coming up with. So 0.0 is 22. 0.1, we came up with, what was it? Yep. Point 2, same x, right? 3.875. And then we add 9.125. Cool. Now we got to go to 0.3. Oh, here's an important note, by the way. On the next block that we just did for 0.2, we don't have to input the x coordinate. You see that? Right, since it doesn't change, you don't have to put in there. That you can, but what am I doing? Oh. This. All right, we're looking for 0.3 here, right? Our y is not going to change, correct? So now we need to figure out, yeah, 2.5 inches plus half the tool, correct? That's all we need.
So that's 2.5 to the center of the circle. You're not going all the way over. So then you have 1.5 and you have to add. Because that 2.5 is the center of the circle. So then 1.5 plus.
Yeah, so it would be 2.5 inches. Minus 1 would put us here. Plus 0.125, half the tool, correct? Plus this little area here, right?
Which is another half. So then basically you end up adding 0.25.
Right. Yeah, but broken all the way down, this is what it looks like, right? So you got 3.5, or no, 1.5 plus 0.25, so it'd be 1.75. That sound right? Right, so we need, add that to the y coordinate. So well, we know we need to move this way 1.75 inches.
So then we got type 3 would be
You just move that.
yeah.
So 3.875 plus 1.75.
5.6.
3.8. 5.625.
5.625. Correcto. Okay. Now we need to,
We improve that number.
you want to do another one? The next one's pretty easy. I mean, all we're doing is we're moving 2 inches minus the drill bit. So the next one would be adding to the x direction 2 minus 0.25, so it'd be 1.75, right?
Wouldn't it still need to be the full?
Yeah, 2 minus 0.25, right? Or 2 minus 0.175 minus 0.175. So we're going to go add 1.75 to this, right? So then it'd be, the next one would be 0.75. So it'd be 6.7 point. Same Y. Yeah, P5 would suck. Because you're going 2.5 minus this distance plus this little thing that we figured out earlier. Because this is a 45, that means this has to be a 45, right? So that extra distance is going to be the same as this extra distance here. So the good thing is that once you figure that out, if you're writing all this down, all you're doing is plugging and chugging. But I don't really care to walk through 0.5 unless you guys feel like you need to. That's okay. All right. I don't think the ICC carving lab is this complex, but yeah.
We did in high school, we figured out we kind of tweaked the system. Figured out automatic ways to pop information back on.
Oh, really?
The professor never knew. Like, hey, these are some good points here. They just draw on it.
All right. This just breaks down, you're telling it circle interpolation, counterclockwise coordinates. And then these are the numbers I think we just came up with. I took them all.
That's for circle. Okay.
So you're telling it to move to these coordinates, which we figured out, X and Y, right? And then you're telling it where the coordinates of the center of the circle is, so it knows how big to make that arc. Linear interpolation, target coordinate, its Y is unchanged, so that's going to 0.5. Linear interpolation targets, target coordinates, C step 3, going back to 0.1. Target coordinates, linear interpolation, end of data. And all we're doing there is telling it to go back to 0.0. And then M00 program stop. Ooh, you guys think you can do that? You want to do your initials instead of ICC? No, let's do ICC because everybody's got to do it the same because we got to come up with the same numbers, right? I think there's just some plexiglass back. I'll have to look. Those machines aren't even powered up yet. I don't have that lab ready to go. But running through those G codes will be helpful when you're doing these first labs on the, hopefully at least one of those machines will be back up and running Friday. But Friday's a lab day, right? Yeah. So that means Monday. Guess I got the weekend to get those other machines up and running for Monday. You gonna leave today knowing more about CNCs than you came in with?
Sure.
What I already knew.
Success.
There you go.
Definitely.
Well, Gold star, you taught us something.
I just want you guys,
Congratulations, you did your job.
I just want you guys to be happy.